Imagine you're booking a holiday. The system reserves your flight, then it charges your card. Then it tries to book the rental car and fails. A timeout, a database error doesn't matter. Your flight is reserved, your money is gone, you have no car, and nobody told you. From the flight services perspective, everything is fine. From the payment services perspective, everything is fine as well. From your perspective, the system just ate your money and gave you half a booking. This is the distributed transaction problem, and it's the hardest consistency challenge in microservices architecture. Two-phase commit, the transitional database solution, doesn't work at scale across many services. So what do? You use the Saga pattern, and that's exactly what this video is about. Quick note before we start. This is the third video in a series. We covered retry strategies first, then idempotency. If you haven't watched those, the links are in the description, and idempotency in particular is a hard dependency for Sagas to work correctly. If your Saga steps aren't idempotent, the whole thing falls apart. We'll come back to that in a second. Let's start with why this problem exists in the first place. In a monolith with a single database, transactions are free. You begin a transaction, make changes across multiple tables, and either commit everything or roll back everything. The database guarantees atomicity. Either all of it happened or none of it happened, no partial state. In microservices, we've deliberately split that single database into multiple databases, one per service. The flight service owns its own database, the payment service owns its own database, and the car rental service has its own. It's the core principle of microservices design. Services own their data, they do not share common database across all services. The problem is that a business operation like book a holiday spans all three services, as we saw. And you have no single transaction that covers all three databases. The traditional solution is two-phase commit, or 2PC. In phase 1, a coordinator asks all participants, can you commit? Every participant logs its data and says yes or no. In phase 2, if everyone said yes, the coordinator sends commit. If anyone said no, everyone rolls back. This sounds very easy and fine in theory. In practice, it has serious problems. First, it's blocking. While participants are waiting for the coordinator's decision, the data is locked under high load or long-running transactions. This kills throughput because basically the maximum throughput of the system, regardless of scale events on the microservices side, it is limited by the maximum throughput of the single coordinator. Second, the coordinator is a single point of failure, and if it crashes between phase 1 and phase 2, participants are left holding locks indefinitely. Third, it requires tight coupling between microservices. Every single service must implement the 2PC protocol. You can't mix databases that don't support it. You can't use managed services that don't expose transaction APIs. In modern serverless architectures on AWS, 2PC is essentially off the table. You can't turn a two-phase commit across Lambda functions, DynamoDB tables, and external payment APIs. The alternative is to accept that you cannot have ACID atomicity across services, and instead design for eventual consistency using compensating transactions. That is what Saga is about. A Saga is a sequence of local transactions. Each transaction updates its own services database and triggers the next step. If a step fails, the Saga runs compensating transactions to undo the work done by the previous steps. The critical concept is compensating transaction. It is not a database rollback, it's a new forward-moving transaction that semantically undoes the effect of previous steps. If step 3 fails, you don't roll back step 2 in the database sense. You run a compensating transaction for step 2 that undoes what step 2 did at the business level. If step 2 reserved a flight, the compensation cancels the reservation. If step 2 charged a card, the compensation issues a refund. Let's walk through the travel booking example because it illustrates this perfectly. The happy path has 5 steps: reserve flight, reserve car rental, process payment, confirm flight, confirm car rental. Each step writes to its own DynamoDB table. Each step has a corresponding compensating transaction. Reserve flight step, its compensating transaction is to cancel flight reservation. Reserve car rental cancel car rental, process payment, refund payment. Now imagine payment fails at step 3. The Saga runs compensating transaction backwards. First it refunds payment and cancels car reservation to compensate step 3, then step 2, and after that step 1. The system ends up in a clean state, not the original state exactly. You might have a reservation record with a cancelled status rather than no records at all, but in a consistent, coherent state. This is eventual consistency. It's not instant. There may be a window where the flight is reserved but the payment hasn't been refunded yet, but the Saga guarantees that the system will reach a consistent state. There's one more concept worth naming here, the pivot transaction. This is the point of no return in the Saga, the last step that can be compensated. Everything before the pivot can be undone. Everything after the pivot cannot. In our travel example, confirming the flight with the airline might be non-compensatable. Once the airline has issued the ticket, you can't programmatically unissue it. Design your Sagas so that non-compensatable steps come as late as possible after all the risky steps have been succeeded. There are two fundamentally different ways to implement a Saga, and this is the most important design decision you'll make. First button is choreography. Choreography works through events. Each service does its work, publishes an event, and other services react to the event. The order services publishes order placed, the inventory services listens to order placed and updates stock, the payment service listens to inventory updated and charges the card. No central coordinator, and the services are aware of each other only through the events they publish and consume. The other pattern is orchestration, and it works through central coordination. The orchestrator knows the full sequence of steps. It sends a command to each service, reserve the flight, waits for response, and decides what to do next. If a step fails, it sends compensating commands in the right order to compensate the broken process. The orchestrator is in charge. Services don't need to know about each other. They just respond to commands from the orchestrator. In AWS, the natural orchestrator is step functions. It gives you a visual representation of the entire flow in the console. It gives you built-in retry logic at each step, error handling, and compensation paths as first-class concepts. For serverless architectures in AWS, orchestration with step functions is almost always the right default choice over choreography. You lose some degree of decoupling. The orchestrator knows the full flow, but you gain observability, which in production is worth a great deal. Here's how the AWS architecture looks in practice. API gateway triggers Lambda that kicks off a step function state machine. The state machine is the orchestrator. It defines the happy path and every compensation path in one place. Each step is a task state that calls a Lambda. Each Lambda does one thing, writes to its own DynamoDB table and returns a status. Step functions uses choice states to branch. Success means move forward and error means start compensating. The key thing to understand is that all the branching logic, which compensation runs when, in what order, lives in the state machine definition, not in your Lambda code. Your Lambdas stay simple. The orchestration handles all the complexity. 3 things worth knowing before you build this. Compensation can also fail. Your compensation path is a sequence of service calls, and any of them can fail too. Retry your compensations and make them idempotent. If return refund returns 3 times, the customer gets only 1 refund, not 3, because otherwise you will have to write another Saga to solve the Saga compensation problem. Some steps can't be compensated. Sending a confirmation email, issuing a physical ticket, publishing to an external system. Once these happens, you can't undo them programmatically. Push not compensatable steps as late as possible in the sequence after all the risky steps have been already succeeded. If you send a confirmation email at step 2 and step 4 fails, you've confirmed a booking that doesn't exist. Observability is not optional. A Saga that fails silently is worse than no Saga at all. Step functions give you full execution history, but your Lambda functions should emit structured logs at every step. When Saga fails at step 4 of 7 at 3 a.m., you need to understand what happened in minutes, not hours. Saga is also not about good things, it also adds significant complexity. There are situations where they are the wrong tool. When you have 2 or 3 services, if you are coordinating across 2 services, the overhead of Saga defining compensating transactions, building the state machine, handling partial failures, it may not be worth it. Consider whether you can redesign to have one service call the other synchronously within a single local transaction. Number 2, when you need strong consistency. Sagas give you eventual consistency, not acid. If your business rule is the inventory must be exactly correct at all times, not eventually correct, a Saga will not satisfy this requirement. In this case, reconsider your service boundaries. The fact that you need strong consistency across the 2 services is often a sign that those 2 services should be one service, when operations can be compensated and failures are common. If your Saga has multiple non-compensatable steps and the failure rate is high, you'll be in a state of partial completion frequency with no path back. Design for low failure rates in the compensation required zone or restructure the flow. Before you go off and build one of these, I'd put the checklist on the screen and just walk you through the thinking behind it. The 2 I'd stress most: idempotency at every step, non-negotiable. Step functions will retry and compensating transactions that are themselves retried and idempotent. The rest is really about design discipline before you write a single line of code. Do you know where your pivot transaction is? Have you pushed non-compensatable steps as late as possible? Can you observe what's happening across the whole flow from one place? And honestly, the last question in this list is, do you actually need a Saga here? Or are your service boundaries doing more harm than good? Sometimes the right answer is to merge 2 services and get a real transaction. Sagas are powerful, but they are not free. The complexity is real and it compounds as you add steps. This wraps up the 3-video series on the fundamentals of resilient distributed systems: retries, idempotency, and Sagas. These 3 patterns work together. Retries create duplicates, idempotency handles duplicates. Sagas coordinate across services with the assumption that retries and idempotency are already in place. Thanks that you have watched till this place. See you next time.